Okay. Am I still in frame on the camera?
Yes.
Okay. This is an eigenvector for all occasions, I guess take 2, because the original recording did not have good audio. So what's the goal for the talk? We want to give a high-level overview of how eigenvectors are used in data analysis. This is the original abstract. I guess you guys haven't actually seen the abstract of the talk. This is the original abstract of the talk. So I was claiming that you basically tell me your favorite problem in data analytics, and I'll tell you how to solve it with eigenvectors. And so you can see there's a lot of stuff up here. So we're going to go pretty fast, but you guys have to slow me down with questions whenever I say something that needs a little bit more elaboration. And I'm going to focus on kind of the high level here. I'm going to try and avoid getting too mathematical. We can get mathematical if it makes things easier to explain. But I'm going to try and focus on the intuition of really what eigenvectors mean. So we'll kind of, hopefully leave today with an understanding of what tools exist out there. And if you need to use any of them, you can always look up the math later on as appropriate. So this is about the only, this is about the level of mathematics we're going to be at. So the definition of an eigenvector is important. We say that you've got a pair lambda and x. That's an eigenvalue, which is a number, and an eigenvector pair of a matrix if multiplying x by the matrix only rescales it. It doesn't change the direction of the vector. And so we actually were talking about this beforehand. You can think of a matrix as an operator. It basically, when you multiply a vector by it, it does something to that vector and gives you a new vector. And different matrices do different things to different vectors. An eigenvector is special because it only gets rescaled by the matrix. It doesn't change direction. So it gets rescaled by the eigenvalue lambda. And it turns out that for any square matrix, you can find a set of, if it's an n by n matrix, you can find a set of n of these eigenvalue eigenvector pairs for the matrix. And there's also a generalization that we'll see in a second for rectangular matrices where you kind of get pairs of eigenvectors called a left and a right singular vector. But we'll get there in a second. So that's the definition. But I think the trouble is if you take a linear algebra course, this is kind of what you learn, and you learn how to find eigenvectors. But you don't learn as much kind of the intuition of how they're used and all the cool applications. And that's where we want to focus on today. And I've broken things up into a couple of high-level key ideas. And so the first idea is stationarity. This is kind of what you can see from the definition here. An eigenvector is kind of a stationary vector in the sense that it doesn't change when you multiply it by the matrix. It only gets rescaled. And if the eigenvalue is 1, then it's really stationary because it doesn't change at all when you multiply it by the matrix. And so there's a lot of intuition and a lot of applications just follow from this kind of high-level idea of stationarity. Something being stationary when acted on by the matrix. So let's talk about a couple of those. A lot of these are related to random walks, which you could spend many, many talks just talking about interesting, cool things that random walks give you. But let's summarize how a random walk works. You start somewhere in a network. This could be a graph, a network, or it could be an arbitrary data set. If you just define some notion of how related elements of data are, you can think of any data set as a network. So I start in the upper left-hand corner. And then if I take one step of the random walk, then you just follow a random outgoing edge each with equal probability. So my probability distribution over location after one step of the random walk is this. I have a 1/3 chance at being at any of these nodes right here. And if I take another step of the random walk, then you can imagine each of these 1/3s getting split up and sent out in equal proportions on these outgoing edges in kind of an operation that redistributes the weight. I started with 1 unit of weight or 1 unit of probability, and I always actually have 1 unit of weight or 1 unit of probability because it just gets redistributed at each step of the walk. Now, we can actually model this very succinctly from a mathematical perspective by describing this distribution of weight on all the nodes that sums to 1 as a vector. And one step of the random walk corresponds to multiplying that vector by what's called a walk matrix. It's called a Markov matrix. The entries basically tell you transition probabilities, the probability that if I'm in a certain node, that I move to a different node. And those are just, if I have 4 neighbors, those probabilities are like 1/4, 1/4, 1/4, 1/4. So multiplying a vector by the random walk matrix evolves the vector kind of from its distribution at one point in time to its distribution after taking a step of the random walk. And so if I multiply by that matrix over and over and over again, it turns out there's a really nice result, which there's a little bit of mathematical fine print, but usually this will converge to what's called a stationary distribution. It's stationary because it actually doesn't change anymore after you multiply by the matrix. And if, in fact, I should have fixed this thing on the slide. This should be a 34, not a 35. Oh well. So the stationary distribution of a graph is kind of the limit of this process where you start somewhere and just keep taking steps of a random walk. And interestingly enough, it doesn't matter where you start. So random walks lose track of their history. They all will converge to the same stationary distribution. And in this case, if you have an undirected graph, you'll actually notice that the stationary distribution, the weight of each node, is actually just proportional to its degree. So here I have 4 outgoing edges, and it's 4 out of 34. Here I have 3 outgoing edges, so it's 3 out of 34. It's more interesting in a directed network, where it's not quite as obvious or simple what the weights are going to end up being. But I have the stationary distribution, and this has an interpretation as an eigenvector, because if you multiply this distribution by the walk matrix, it doesn't change. You get the same distribution out. So the weight gets redistributed, but it ends up being the exact same distribution. And that's actually a really nice property of these walk matrices. Any Markov matrix has an eigenvalue of 1, which corresponds to this as an eigenvector, the stationary distribution. All of the other eigenvalues have magnitude less than 1. So kind of their contribution decays away as you keep multiplying the vector by the walk matrix. The only thing left in the limit is the stationary distribution. Now, what are the applications of this? They're actually, yeah, please. Mm-hmm.
Okay. Do you have a real quick definition of Markov matrix? Is that rows and columns?
So either rows sum to 1 or columns sum to 1. In this case, the columns, I think, sum to 1. But you can also define it as rows summing to 1, in which case I think you put a transpose here.
The principal eigenvector is the one with large eigenvector.
The principal eigenvector is the one that has the highest the largest in magnitude eigenvalue, right?
Largest in the lower.
It depends if you have some negative ones. It's clear if all your eigenvalues are non-negative, then it's kind of clear which one's the biggest and which one's the smallest. I'll kind of use the words largest eigenvector and smallest eigenvector to mean the eigenvector paired with the largest eigenvalue or the smallest eigenvalue, just in terms of the number that the eigenvalue is, not the norm of the eigenvalue.
Okay, so we're assuming that all eigenvalues are real here?
In this case, they may not all be real. So you can get complex eigenvalues, but their magnitude in terms of the magnitude of a complex number would be less than 1, except for the one that pairs with the stationary distribution. I won't go too much into like certain properties of matrices and so when the eigenvalues are real and orthogonal. So I'll mention those things if they're relevant, but I won't get into too much of the mathematics on that. So here's what we get application-wise. And there's an important distinction, I think, that we raise on this slide between the principal, or the eigenvector with the biggest eigenvalue, that was that stationary distribution, versus all the other eigenvectors. The principal, the highest eigenvector, usually is kind of special. It usually has a different intuitive interpretation than the other eigenvectors. And in this case, the principal highest eigenvector of a walk matrix has an interpretation in terms of centrality. So each weight here kind of tells you the level of importance or centrality of a node. Like I mentioned, in an undirected graph, this weight is just proportional to the degree of the node. And so it has a very simple interpretation in terms of centrality. So the more neighbors you have, the more important you are, the more central you are. But if it's a directed network, there's also a good interpretation. And in fact, that's the interpretation that Google uses with its PageRank algorithm. So Google PageRank ranks the web by modeling it as a directed graph. Every node is a web page, and it directs to all the web pages it links at. And you just find the principal eigenvector of that enormous, billion-plus node graph. And every node's weight is its PageRank score. And the rationale behind that is if you do a random walk of the web, you're kind of simulating what a random web surfer would be doing, just clicking on random links and going from web page to web page. And if a page has a high value in that stationary distribution, it's presumably a page that a random web surfer would go through, would navigate through often. So it should be important because it's well linked on the web. So it gets returned very highly on your search results. In fact, the Google PageRank random walk is a little different than that. They not only move to a random neighbor, but they also have the option of teleporting. And so the actual Google random walk is maybe with 90% probability, you move to a random neighbor at each step, and with maybe 10% probability, you teleport to a random page. So also modeling the way that a random web surfer would maybe just type into the URL bar, a web page and just teleport straight to it. That's still just a regular random walk, and so the eigenvector, principal eigenvector of the walk matrix for that random walk is your vector of PageRank scores. So Eigenvector is very important here. They launched a multi-billion-dollar company that just uses eigenvectors. So there's a centrality interpretation for the principal eigenvector, but the other ones are kind of, I think, people know a little less about. A lot people know kind of about Google PageRank. The other eigenvectors are a little more mysterious, and people don't seem to maybe know as much about them, but they're almost more interesting. Look at the numbers here. This is actually the second eigenvector in terms of prominence. This is the first, this is the second. What do you think is kind of happening here in terms of what these weights are telling us in this network? I've got these guys seem to have some positive weights over here, and these guys over here have some negative weights. What does that seem to be indicating in this network? Clusters, yeah. So actually, each of the non-principal eigenvectors kind of has an interpretation as suggesting a way that you could split your graph into a pair of clusters. It's kind of you've got the nodes that have more positive weight and the nodes that have more negative weight. And there's actually quite a few ways to make sense of that, to rationalize that. One of them is from stationarity. So if you think about things, this is a stationary vector. If I multiply this by the walk matrix, if I take one step of a random walk and redistribute the weight accordingly, then I get out the same distribution, but just rescaled. And if the eigenvalue is big, it's still, the distribution is still mostly still there. It doesn't get decimated by too much. So imagine what happens if this is a pretty big cluster, and this is a pretty big cluster, and there's not a whole lot of connectivity between, which is usually the case with clusters. Then when I redistribute all this positive weight, it kind of reinforces itself. And the negative weight here gets redistributed mostly within the cluster. And so this cluster also stays mostly negative. There's not a lot of crosstalk. There's not a lot of cancellation that you would get by the positives and the negatives mixing together. And so that stationarity kind of implies that the weights that you get out should kind of reflect some sort of mutually reinforcing clusters. All right, the positives are mostly connected to positives. The negatives are mostly connected to negatives. And so that kind of the intuition kind of follows, I think, from stationarity. Another nice way that you can kind of argue that this should result in a good pair of clusters is there's a prominent cut problem called the normalized cut, which is, unfortunately, it's an NP-hard problem. It's very hard to solve it exactly, but we can relax the problem to a problem that this is the optimal solution of. And you can see that what I mean by a relaxation is when you ask for a partition of a graph, you're kind of saying, I want some nodes on the left side and some nodes to be on the right side. This is kind of a continuous version of that. The nodes have real valued weights, some being positive and some being negative. So it's kind of more of a fuzzy, continuous clustering that we're getting here. It's not not zeros and ones. But if we relax the problem, it becomes easy to solve, and the answer turns out to be an eigenvector, and we'll kind of see why later in the talk. Normalized cut is a really sensible cut objective function for partitioning a graph. It basically asks you to partition the graph into two pieces such that you minimize the probability that a random walk transitions back and forth between the two. So if you think about what a random walk is going to do, if your graph does have two prominent clusters, most of the time the random walk is going to be walking within a cluster, and not too much time it's going to be walking between the two clusters. And so find me two clusters such that you minimize the probability of stepping kind of between the two. That's kind of what normalized cut is asking. And a relaxation of that problem gives you this as a solution. Was there a question?
Yeah, so everything you say appears to apply to the principal eigenvector too. Why doesn't principal eigenvector produce clustering and the second eigenvector does?
So mathematically, there's something called the Perron-Frobenius theorem, which says that if you take a matrix that's non-negative or I think positive, then the principal eigenvector is guaranteed to have non-negative entries in it. So it kind of looks special. All the other eigenvectors, they have to be kind of orthogonal to this one, and so they have both positive and negative entries. And so the principal eigenvector is usually, in many cases, it's non-negative. And so it's a little harder to interpret as a pair of clusters, whereas these other eigenvectors have a distinct positive and negative end to them.
And so the reason we expect to see our clustering on the second and not third eigenvalue is because the second is going to be like our...
The second is like the best one, but the third would also suggest a different two-way split. The fourth would suggest yet another two-way split. Every non-principal eigenvector suggests a two-way split, and the corresponding eigenvalue kind of tells me how much I should believe in those splits.
Is direction of maximal variance the thing? That would explain it?
We'll kind of get there as well. So when we talk about principal component analysis, there will be another interpretation of this result. So, okay.
I have a question about relaxation. When we relax it, we convert them to integers or positive, negative?
Well, the original problem would be kind of like saying, solve this problem with these weights being like either -1 or +1, you know, because you're either on one side or the other, and you relax it to allow the weights to be continuous, and that lets you solve the problem more effectively. Okay. So here's a direct application of that. A lot of times in graphics, we can solve image segmentation problems by solving graph partitioning problems. This is my cat, Nano, who has graciously allowed me to find her eigenvectors. And so what I've done is I've turned the image into a graph in the natural way where every single pixel turns into a node. And you just take every node and connect it kind of to a bunch of its nearby neighbors. The weights of the connections have to do with the difference in color or black and white intensity between those neighbors. So you get a graph with edge weights, and then you can find its eigenvectors according to what we just talked about. I've omitted the principal eigenvector because remember that one's usually special. It talks about centrality, so that would probably have high weight around Nano's nose and low weight around the periphery because that's the center of the graph more or less. This is the second, the third, and the fourth eigenvector. Right here what I've done is I've coded it from like the highest negative weights to the highest positive weights kind of in grayscale, and then here I showed you what happens if you just cut the negatives versus the positives. Kind of what's the cut suggested by each of these eigenvectors. And you can actually see that eigenvector number 4 actually correctly partitions the cat from the non-cat, which is all we can hope mathematics will ever do for us, right? The other eigenvectors, we will kind of get more of an intuitive sense of what they are trying to do. In fact, let me talk about that right now. These eigenvectors are basically, they're kind of like vibrational modes, they're waves. Kind of, if you imagine kind of like take the graph here, the picture of Nano, and like shake it like a tablecloth, then if you shake it at just the right frequency, there's going to be kind of like a standing wave that develops in the tablecloth. So this is kind of like basically like a standing wave that's kind of vertically oriented. This is a standing wave that's kind of horizontally oriented. This is, if you shake the tablecloth at just the right frequency, then a cat and an anti-cat kind of keep alternating back and forth. But if you look at the further eigenvectors, they're going to start looking more checkerboardy because they're kind of higher frequency waves. So eigenvectors have an interpretation as vibrational standing waves. We'll get to that actually later on as well. But that also kind of helps just explain the intuition behind what these are doing. This would ideally just be a straight vertical cut and a straight horizontal cut, but there's a cat that's kind of messing with things a little bit. So image segmentation, good application. Here's another kind of thought. We're still on the page rank stationary distribution sort of line of thought. Everyone is generally comfortable with the notion of a Gaussian distribution. It basically is a distribution of weight that's centered on a particular point. So sometimes you might call this a kernel. It kind of tells you how to take a single point in space and smoothly distribute weight so that it's concentrated around this source point. What's the analog of that in a graph? So what if I want to draw a Gaussian distribution around node X? It turns out that we can develop kind of a well-founded notion of that and make what sometimes is called a diffusion kernel. There are different names for it. The word diffusion kernel kind of evokes this idea that maybe you're pumping some sort of viscous fluid into node X, and some of it kind of dries and sticks to X, like you're watching paint dry, and some of it kind of oozes out to the neighbors of X, and some of it dries on the neighbors of X and then oozes out to their neighbors. And so if you look at the overall distribution of that viscous fluid at the end of the day, it's highly concentrated around X, but also probably highly concentrated around nodes that have a lot of connectivity because there's a lot of ways to reach them. And so we can actually phrase that as a random walk process where sometimes it's called personal PageRank, where you basically start a random walk at X and you do the Google PageRank algorithm, but when you teleport, instead of teleporting to a random node, you teleport back to X. And so you can imagine what that's going to do to the stationary distribution of the random walk. Because you always teleport back home, it's going to kind of bias the distribution to have a lot more weight in the vicinity of X as well as around nodes that have high centrality. And so imagine if X is your home page and you do this, maybe it gives you a version of Google's web search that is kind of more personalized to your interests. That's why it's called personal PageRank. So it's really nice. This is kind of a good way of giving us kind of a distribution that's basically it's kind of centered on node X. And there are lots of useful applications of this. So how similar is node X with node Y? If they're not directly connected, how would you kind of characterize similarity between two nodes? Well, you could run personal PageRank starting at X and look at what weight it assigns to Y, and that tells you some notion of similarity. Okay. Lots of applications of this. You could think about a recommendation system on Amazon.com. It always recommends that I should buy things that I haven't bought, so there's no direct edge between myself as a user and a prospective purchase. But nonetheless, Amazon knows that I'm interested in this because people who have bought similar things to what I've bought have bought that object. And so if you run personal PageRank, starting from a user, then it will generally assign weights that are really high to purchases not only that you've made, but purchases that you ought to make, that are highly connected to you in the network structure of this bipartite graph right here. So lots of people who have bought similar things to you have bought that object. So this could be used in recommendation systems. It also could potentially be used, I don't think this is particularly common, but just to kind of show you ideas, in imputing missing data. So if I have a standard data matrix here, this is the typical way that we think about data matrices in a lot of applications. We have n elements of data, which are the rows of the matrix, and each element of data is characterized by a feature vector, d features. So like the height, the weight, or if these are different genes, n different genes, you could measure the level of expression of the gene in d different experiments, and that's a feature vector that characterizes each element of data. Another way to think about this sort of matrix is in its bipartite graph form. So the nodes on the left are the rows, the nodes on the right are the columns, and the weights of these edges are just the weights in the matrix. And if I have missing values in this matrix that I want to guess what should go there, my experiment failed, how do I impute missing data? Well, I could potentially run some sort of process, kind of like personal PageRank, that might be able to infer what a missing link should be. I think probably more commonly people use things like low rank approximations, which also use eigenvectors to find missing data, which we'll also talk about in another slide. So lots and lots of applications of sort of random walks, PageRank type algorithms, but this is all kind of based on the notion of stationarity. Yeah?
You earlier, I think 2 slides ago, put a little footnote that it's only stationary. You only see stationarity if it's non-bipartite.
Yes.
Bipartite graphs.
So if you're so the fine print, some of the fine print about reaching a stationary distribution, if your graph is bipartite, so bipartite is
it oscillates, right?
Is this, then you kind of get 2 stationary distributions, because you can imagine if you start on the left, then every step you transition from one side to the other, so the parity of the number of steps matters. And so if you have kind of like an even stationary distribution and an odd stationary distribution, so you actually end up with 2 principal eigenvectors, one with eigenvalue 1, one with eigenvalue -1. And so, but most graphs are not, unless they're deliberately bipartite, they're not bipartite. And they have to be connected, because otherwise, if you have a disconnected graph, you also get multiple stationary distributions corresponding to each of the connected components. So there's a little bit of mathematical fine print with some of this stuff, but usually it doesn't mess with the intuition too much. Okay, so idea number 2, kind of we're transitioning to kind of another way of thinking about things. That's another way that we can kind of get eigenvectors in different applications. And that is expressing a matrix as a combination of what we can call outer products. An outer product is a really intuitive notion. It's basically I take a vector kind of and assign it to the rows of a matrix, and take another vector and assign it to the columns. And here I've kind of depicted the vectors as going from large numbers to small numbers and large numbers to small numbers. And I just take all the pairwise products of those entries in those vectors, and I get the contents of this matrix. In probability theory, you might see this if you have a joint probability distribution between 2 independent random variables, then it can be factored into 2 marginal distributions like this. But this is a really common sort of thing that we see in many applications. So the matrix has really large numbers here because these are the products of large numbers in this vector and large numbers in this vector. And there's also large numbers here because it's the product of very negative numbers on this side and very negative numbers on this side. So outer products, if you look at them visually, they have this sort of kind of block structure to them. So the big numbers and the big numbers kind of give you a block, and the big numbers and the little numbers give you a negative block, and so on. Block structure in matrices can be pretty useful, and we'll kind of talk about why in a second. But it turns out any matrix can be decomposed via its eigenvalues and eigenvectors into a combination of these outer products scaled by eigenvalues. So if you have a square matrix, you can decompose it into the first eigenvalue, and here typically the convention is you list them in decreasing order, so the biggest eigenvalue is first, second biggest eigenvalue. So this is kind of the most prominent contribution towards A. So first eigenvalue times an outer product based on the first eigenvector, second eigenvalue times an outer product based on the second eigenvector, and so on. And you have n of those terms. If you have a rectangular matrix, the same thing works. It's just you use these pairs of eigenvectors from a singular value decomposition. So you have, again, first eigenvalue times an outer product based on the first pair of eigenvectors, and so on. So in any case, we can decompose a matrix. We can therefore kind of think of a matrix as a much simpler sort of way. Multiplying a matrix by a vector, what does that do? Well, you can think of that process more simply in this representation. So take A times X, what does that do? That's the same thing as taking this times X plus this times X plus this times X, and so on. What does it mean to multiply this by X? What's the action of an outer product like this on X, on a vector? If I have an outer product of like X1 times X1 like this,
Projection.
It's a projection along X1, exactly. And so multiplying by this projects you along the x1 direction and scales you by lambda 1. And so you can think of the action of any matrix as taking, if I act on a vector, I take the amount of the vector that points in the x1 direction, the projection along x1, and I scale that by lambda 1. And then I take the part of the vector that points in the x2 direction, I scale that by lambda 2. So multiplying a matrix by a vector kind of emphasizes the parts of the vector pointing along its prominent eigenvectors. Okay. So in terms of applications, though, there's a lot of applications here. One is I can actually just cut this off at some point and approximate my matrix by the first couple of terms here. And this is exactly what we're going to do with like principal component analysis and other techniques. If these eigenvalues are such that you have like a big eigenvalue, and then a bunch of small ones from then on, then your matrix is really well approximated by just two terms like this. And you don't lose much by truncating it and getting rid of everything else. In PCA, that's going to correspond to like projecting your data down to just 2 dimensions. And so you can get what's called a low rank approximation of your matrix that way. This is also how we can sometimes impute missing data, is to kind of find low rank approximations to a matrix. But there are lots and lots of applications for doing this. Let me switch to the next slide just to kind of show you. A lot of times if you take up a journal in biology or some other discipline where they've analyzed data, you'll see pictures like this, where they've got your standard data matrix. Every row is an element of data with D columns that correspond to the features, the dimensions of the data. And they've arranged the matrix in a very pretty way. So they've ordered the rows and the columns of the matrix to make the structure of the matrix kind of look nice. In fact, they try and make it look kind of like a block matrix if possible. How do you do that? How do you take an arbitrary matrix and reorder it so that it looks really pretty like this? Well, what you can do is think about this decomposition. Each one of these terms is suggesting that this is basically showing that your matrix is made up of these. It's made up of a combination of these, this being the most prominent. And so if you just look at the most prominent, the largest eigenvector, and you rearrange the rows and the columns of your matrix according to the ordering of the weights in those eigenvectors, your matrix would look like this if you were just viewing that outer product. And since you're saying that was the biggest contribution to the matrix, if you reorder it that way, that usually makes your matrix look relatively pretty, especially if your matrix really does have kind of a very prominent contribution from the first part and not so much from the other parts. If your matrix has a prominent contribution from all of these terms, then reordering it, maybe it'll look a little bit muddier. But this way we can reorder a matrix to make it look nice. We can also do what's called biclustering, and this kind of is related to our earlier discussion when we looked at the non-principal eigenvectors. They had a positive and a negative end, which corresponded to kind of two sides of a perspective clustering. We can do the same thing here, only we get biclusters. We actually simultaneously cluster the rows and the columns of a matrix. So in data analysis terms, we're clustering whatever the objects are, the elements of data, and we're clustering the features of our data set in a mutually reinforcing way. And so we're trying to kind of make our matrix look like a block like this. This is kind of what a bicluster looks like. You have a group of related elements and the features according to which they're related. And then you also have like the negative ends which also mutually reinforce each other. So these elements and these elements kind of form a bicluster, a perspective bicluster, because it's elements of data and features that mutually kind of form a reinforcing block. So if you can find block structure in a matrix like this, that usually means you're finding clusters, or more accurately, biclusters. And so the singular value decomposition can help you do that by kind of thinking in these terms. So every single one of these blocks gives you a prospective biclustering solution, and the value of the corresponding eigenvalue tells you how much you should believe in that solution. So the ones with really big eigenvalues, they contribute a lot, so those probably are more prominent potential solutions. All right, and then remember again, the principal eigenvector is usually special. So if your original data matrix A was non-negative, that means invoke the Perron-Frobenius theorem, you're going to get principal eigenvectors. The very first term here is going to be a block matrix that you get from a product, an outer product of two non-negative vectors. The rest are going to have pluses and minuses, and they have a biclustering interpretation. But the principal one has a wonderful, wonderful interpretation in terms of kind of pairwise reinforcing centralities. And so what you end up getting is weights assigned to the rows and weights assigned to the columns in kind of a mutually reinforcing way that reflects centrality. So you get whichever rows are the highest weight are like the most important rows. So you're kind of doing, finding the most prominent objects. And then the columns with high weight kind of correspond to those rows. Those are like the most interesting features. So you can actually do like feature selection using eigenvectors, using that principal eigenvector. If you think about it in terms of this bipartite graph representation, you're basically putting weights on the objects, the rows, and weights on the features, which are the columns. They're all non-negative, and they have kind of an importance or centrality interpretation, and they reinforce each other. So a feature is important because it's used in a lot of important objects, and an object is important because it incorporates a lot of important features that kind of reinforce each other. There's a wonderful paper by John Kleinberg that actually uses this same idea for web searching, kind of as an alternative to Google. It's called the HITS algorithm, and it actually gives every web page 2 scores. So you kind of have your score as, well, you start with a matrix that's basically describing all the links on the internet, and the rows and the columns have the interpretation of each row kind of tells you a web page in its role as a source web page, and each column tells you each web page as its role as a destination page, because each link goes from a source to a destination. And so you actually, the weights that you get, you can actually think of it as assigning a weight to 2 weights to the same page. You get kind of a weight for a page in terms of how well it acts as a source for outgoing links, and you get a weight assigned to a page that tells you how well it acts as a weight for incoming links. And Kleinberg calls these 2 roles of a page hubs and authorities. So a hub is a web page that has a lot of high-quality outgoing links. So it would have high weight here on the left-hand side. An authority is a web page that has a lot of high-quality incoming links. So it's a page that, like a Wikipedia page, that everyone cites. And so that would have high weight on the right-hand side. And so it's kind of a cool algorithm because it gives you kind of not just one weight for importance, but kind of 2 different weights that have interesting interpretations. If we use this like to analyze sports teams, it's like separately analyzing your offense and your defense and giving them separate weights. Okay. Yes?
Give me a little bit more detail on how we would order the rows and columns of a matrix. Is that like dot product with first eigenvalue?
It would be, you look at this very first term. Well, I guess we can look at that. Suppose it was a rectangular matrix. We look at this very first term, and you look at the principal eigenvectors for the rows and the columns. You just look at the way the entries in those eigenvectors are ordered.
Oh,
so you sort the rows and columns so that those principal eigenvectors would end up sorted, and that's what you do. Okay, so lots and lots of cool things that you can get using kind of this outer product mentality. And then just think of this picture. Any matrix can be represented by just a stack of superimposed weighted combination of these guys. All right. Idea number 3. We're doing good here. This might be the most prominent way that we get eigenvectors as the solution of different types of problems. It's by minimizing or maximizing what are called quadratic forms. And a quadratic form is actually, it looks like this. It's kind of like X transpose AY. or X transpose AX if we're dealing with a square matrix. It's a really simple notion. In fact, if we go back to our outer product, if the A wasn't there, this would just be an outer product basically. But since A is here, what we end up with is kind of an outer product of all the pairwise products of things from the row vector times things from the column vector, but they're just multiplied by elements of A as coefficients. So it's basically a weighted outer product. You can think of it that way, where the matrix A gives you the weights. All right. And so this outer product eventually just boils down to a single number, though. So you just take the sum of row times column times Aij, summed over all the Aij's, and that's the value. So what you get out from a quadratic form is just a single number. I like to think of this as kind of the matrix vector version of just like ax squared. We're all comfortable with like constant times a variable squared. That's basically what this is. Just when we talk about grown-up things like matrices and vectors. Now it turns out that if you constrain these two vectors x and y to have unit length, then you can minimize or maximize a quadratic form with an eigenvector. Eigenvectors optimally solve that problem. So either the largest or the smallest eigenvector, or pair of eigenvectors in the case of a rectangular matrix, will minimize or maximize these quadratic forms. And so any problem that you can express as minimizing or maximizing a quadratic form, the answer is an eigenvector. And there's a lot of these problems. So principal component analysis, we'll talk about that in a second. Lots and lots of problems involving cutting graphs or partitioning graphs. There's a really popular objective called modularity, which I actually don't have a slide on, but you can look it up. It's really nice. Highly recommended if you're trying to do clustering that you look this up. It basically tries to find kind of the most surprising cut in a graph relative to a random graph. And it turns out that modularity is NP hard, but you can relax it to a problem where the objective is a quadratic form, and you maximize that by just choosing an eigenvector of a certain matrix. And that kind of gives you, like we saw before, a set of weights for the nodes on your graph, some positive and some negative, and that suggests a good way to split your graph that will usually do a good job with respect to the modularity objective. There are lots of other cut objectives. We talked about normalized cut before. There's one called ratio cut that I'll talk about in a second. They all are NP-hard problems, but you can relax them to problems where the objective is, again, maximizing or minimizing a quadratic form. And so the optimal solution is an eigenvector. We'll see ratio cut in just a second. And then finally, we'll also see an example called spectral embedding. So projecting data sets down to low dimensions, kind of related to PCA again. Again, they all relax to these quadratic forms. In fact, most of these problems are related. We'll see in the next few slides what look like several different problems, but they're actually really kind of just the same thing. So, and hopefully I can emphasize that. So let's look at a toy example. This is a problem that involves projecting a high dimensional data set down to a low dimensional representation. Lots of reasons we would want to do that. And we'll kind of talk about that a little bit more later, but let's suppose, just for the sake of simplicity, that I want to project down to one dimension. The mathematics is the same in 2D or 3D or whatnot. It's just you get more complicated things like matrices instead of vectors. So I'm just going to focus on projecting a high dimensional data set down to one dimension. And so there's a really clean way to think about doing this, where I just want to take every object in my data set and assign it to a position on the number line. So I just want to embed an element data set onto the number line. And I want to do that in a way that similar objects end up close to each other and dissimilar objects end up far away from each other. And so what would be the point of doing that? Well, I guess one nice application is actually sequencing or ordering. If you want to order n things in a natural way, then embedding them in this way on the number line can tell you how to order them, how to arrange them. Kind of similar to how we rearrange the rows and columns of a matrix, I guess. But what's a reasonable objective to minimize or maximize to do that? This is perhaps the most common one. It's sometimes called the squared wire length objective, where you have all of these quadratic terms for all the pairwise interactions of the elements, and you get a big penalty if you have two elements that are really similar. So you have this similarity matrix. Aij is the similarity between I and j. If this is a large number, then you get penalized really bad if you embed xi and xj far apart from each other. So this objective, if you minimize it, strongly incentivizes similar items to be embedded close together, because otherwise you get hit with a really bad quadratic penalty for embedding them far apart. Okay, so we want to minimize this. This also has a nice physical interpretation as minimizing the potential energy of a set of springs. So if you take a spring, imagine a spring that wants to have length 0, very, very short spring, and if you stretch it out, how much potential energy is in that spring? Well, so the potential energy in a spring is the square of the deformation from rest length times the spring constant. So you can imagine if you have two similar elements of data, you connect them with a really stiff spring that resists pulling outwards, and so it has potential energy with a big spring constant times the square of the distance you've pulled that outwards. And you want to minimize the potential energy of this entire system after the embedding of all the springs. So spring embedding is a very common way that we take data and embed it spatially. We have to impose a couple of constraints to make sure that we don't get a trivial solution here, because I could just assign everything to 0 and get a minimum of 0, which would be a trivial solution. So I'm going to insist that the vector x of all my positions has to have unit variance, just to kind of ensure there's a little bit of spread. I can't just embed everybody at the same point. And let's also assume that the vector has 0 mean. So this is a really clean formulation for one-dimensional embedding, sequencing, ordering problems. Basically find a minimum potential energy configuration that has 0 mean unit variance that minimizes this quadratic function. And as you might suspect, you can do a little bit of algebra and express this exact objective as a quadratic form. So it's x transpose times L, which is the so-called Laplacian matrix of A times x. The Laplacian shows up a lot. It's a very famous matrix in kind of eigenvector-based, especially analysis of data. But it shows up in a surprising number of places. It's a very, very powerful notion. It's a simple matrix. It's basically kind of like negative A, except the diagonals are the row sums of A. That's the definition of the Laplacian. I could spend probably 15 minutes just kind of motivating where the Laplacian kind of comes from and why this makes sense, but I don't want to go there for this talk at least, because I want to kind of focus on the intuition. But one property of the Laplacian that's important is that its lowest eigenvalue is 0, and the lowest eigenvector is kind of dumb. It's just the vector of all ones. It's a constant vector. And so if we're trying to minimize this quadratic form, normally the right answer would be the minimum eigenvector, the smallest eigenvector, which is the vector of all ones. And we actually can't use that because I wanted to have a solution of this problem that has 0 mean. What does having 0 mean mean? It means basically your sum is 0. If you take the sum of a bunch of things equals 0, that's the same as saying that the dot product with the vector of all ones has to be 0. So 0 mean actually means that you are orthogonal to the vector of all ones. And you certainly, so we can't use the vector of all ones as our answer. We need an answer that's perpendicular to that vector. And so the next best vector is the second smallest eigenvector, which is so important it actually has a name. It's called the Fiedler vector. And it turns out that's the optimal solution to this problem. It's the second smallest eigenvector of the Laplacian. You'll kind of notice that, remember before that the first eigenvector, the biggest eigenvector, was special, and so we kind of deferred to the second, the third, and the fourth. Same thing here with the low eigenvectors of the Laplacian. The lowest one is kind of dumb. It's all ones. And so we care about the second lowest, and maybe the third lowest and fourth lowest. Those are the ones we really like. In fact, mathematically, the low eigenvectors of the Laplacian are sometimes the same or play a very similar role to the high eigenvectors of A. In spirit, they kind of behave the same way. So where we were previously talking about the top eigenvectors of A, it's the bottom eigenvectors of L that we care about. And for the same reason as before, we kind of sometimes exclude the very lowest eigenvector of L. Okay, so if I solve this problem, that will give me the second lowest eigenvector of L. That assigns weights to all the nodes in my graph. Here's an example of that. Using the same graph that we just talked about, I have embedded it on a number line by assigning each node a position, which is its weight in that second smallest Fiedler vector. And look what happens. I get a reasonable embedding of the graph, but that also has this nice kind of negative side and positive side, kind of this clustering interpretation, exactly like we had before. And it turns out that this is also, it turns out this exact problem is a relaxed version of the NP-hard ratio cut problem. So if you started with this ratio cut problem, which I won't define, but it's also a reasonable objective for cutting a graph into two pieces, and I relax it to a continuous version, it relaxes to exactly this problem of minimizing a quadratic form, this quadratic form, which is interesting that it's the same problem that we ended up with this original motivation of embedding. So we could have kind of gotten here by starting with ratio cut and relaxing it, and we get here, and then suggesting this as a heuristic for how to cut a graph, or we get here as starting from the idea of how do you embed a graph on a one-dimensional number line. So these things are nicely connected as problems. So again, we sort of come back to this idea of if you can project a graph onto one dimensions, great. You can cluster by cutting it. You can do ordering. There's a lot of applications here. You can actually do this in more than one dimension. So this is using the second lowest eigenvector of L, but the third lowest and the fourth lowest also tell you some interesting information. And you can even use those for different coordinates. So, actually, I'll come back to this. This is the wave interpretation, so I'll get back to that. This is how linear algebra thinks I should look. This is a graph of my face. This is a two-dimensional embedding of that graph using the x-coordinates of the points are the values that I get from the Fiedler vector, from the second lowest eigenvector of the Laplacian. The y-coordinates are from the third lowest eigenvector. So if you want to come up with a multi-dimensional embedding, you can take coordinates from those successive eigenvectors and usually get something pretty reasonable. If I wanted just a one-dimensional embedding, then just project everything down onto the x-axis is what I would get. But who wants to one-dimensionally embed that? That's, yeah. You start with a Clemson tiger paw. It gets a little weirder. But so you can make two-dimensional embeddings. You can make three-dimensional embeddings. These are called spectral embeddings sometimes, using this kind of Laplacian-based eigenvector approach. So very cool. Let me now kind of give you, I'll go back to the wave example. I talked before about these eigenvectors, especially like not the principal eigenvector, but like the second, the third, the fourth. They represent kind of vibrational modes or standing waves in our data set. Let's kind of treat that with a little bit more respect now. So if I take a really simple graph, just a bunch of nodes in a row, and I find the eigenvectors of the Laplacian, this is the lowest eigenvector. Remember that was boring? It was just constant all the way across. This is the Fiedler vector. This is the second lowest eigenvector. It's a wave, a standing wave that kind of gradually goes from small up to big. So in our data set, we get this wave from kind of small numbers up to big numbers. If I look at the next few eigenvectors, they are actually cosine waves of increasing frequency. And that's a very good intuitive way to think about these eigenvectors of graphs and of Laplacians. And I guess of the original matrix too, if you look at the top eigenvectors. They represent kind of standing waves. So if you take your graph and you shake it like a tablecloth, then you get kind of these standing wave patterns. And if you shake it really, really hard, then you get a higher frequency sort of standing wave pattern. And that's what you end up getting as your potential cuts. So that's why we look at the Fiedler vector. That's probably the best example of how to cut your graph because it gradually kind of goes from small up to big. So it kind of gives you two nice clusters. It wouldn't work so well to use a much higher eigenvector because the weights would kind of oscillate back and forth between low and high and low and high. So that's kind of why we focus on the nice low frequency waves from the Laplacian. Okay. Actually, I'll kind of tell you, let's just kind of high-level interpretation of why that works, why this standing wave interpretation, because the mathematics is actually not too crazy, and it makes a lot of sense. So remember that our objective was to basically minimize x transpose Laplacian x, this quadratic form. That was the potential energy of a spring system. That was the physical interpretation. If you take the derivative of potential energy, that's actually a vector of the negative forces that are acting on objects in your system. And the derivative of this is just minus Laplacian x. Okay? Or if you look at the forces, it's minus Laplacian times x. So this is a vector of all the forces that are acting on the nodes in our graph in our one-dimensional embedding. And if you want a system to kind of exhibit oscillatory behavior, the system should kind of be modeled like this. You should have your second derivative equals some sort of negative constant times your position. If you solve this differential equation, you get out sines and cosines. This thing will kind of oscillate back and forth. So if you want to have any sort of standing wave or oscillatory behavior in a system, the system has to have this sort of property to it. And so if we write that for our system, we need acceleration is equal to negative constant times position. What's your acceleration? Well, this is force, and force is mass times acceleration, thanks to Newton. So if we just equate that with a constant times x, we see that actually our equation here, which should look very familiar, this is the equation that defines an eigenvector. That's the same equation that defines oscillatory behavior. And so if you look at this, you see that eigenvectors actually are the solutions that give you oscillatory behavior in a spring system. And so if you think about modeling a data set or a graph as a system of springs, then the standing waves in that system are the eigenvectors. Okay, so there's kind of a very physical interpretation of these things. All right, we're almost done. We have, so principal component analysis is another good example of this. This is a well-known technique to people who analyze data, where the idea is you want to take a high-dimensional data set and again map it down to a lower dimensional representation, which we've kind of been doing already. And in fact, the math we've done already basically is PCA, just kind of viewed from a different angle. And so why do you want to reduce the dimensionality of a data set? Well, it makes your algorithms faster because things run faster in lower dimensional spaces. Noise reduction is important. A lot of times your data more rightfully lives in a low dimensional subspace, and the only reason it has higher dimensions is because you have a little bit of noise kind of poking out in other dimensions. And so if you reduce the dimensionality in a good way, you can actually kind of clean up the data by getting rid of some noise, averaging away noise in the data. And then finally, visualization is a lot easier if you can project your data down to 3 or 2 or whatever dimensions. So lots of reasons we want to reduce dimensionality. And principal component analysis is probably the most popular way of doing that. It has a really nice kind of graphical interpretation where if you take a data set, here's a data set, then principal component analysis asks us to come up with a low dimensional embedding. And for simplicity, again, let's focus on just a one-dimensional embedding. So basically embed the data onto a number line, which here you can describe as a subspace. It's just a line that goes through the origin. So take my data points, project them down to a single one-dimensional subspace, and I want to do that in a way that captures the most variance in my data. In fact, there's 2 ways to phrase the objective of PCA. One of them is, if I project my data down to this one-dimensional subspace, then the result should have maximum variance. And by variance, I mean if I project a point down, then it lives now in one dimension at, I guess, this point. So its coordinate would be this green line right here. And so the variance of all the points after projection, that's basically the squares of these green segments. All right, that's kind of the squares of how far they are from the origin. I want to maximize that. I want to capture as much variation in the data as possible. So find me the axis, the line that captures the main component of directionality in my data set. I can also talk about minimizing the error of the projection. So if I project onto this subspace, then I look at the kind of orthogonal amount that this point projects. That's this red distance right here, and square that. That's kind of the squared error of projection. If you add that up over all the points, I want to minimize that. So each point should travel a minimum distance towards its projected value. And it turns out that maximizing the variance is the exact same thing as minimizing the squared projection errors, thanks to just the Pythagorean theorem, because this is a right triangle right here because you project orthogonally to the subspace. So the red squared plus the green squared is equal to the square of the hypotenuse. So if you maximize the sum of the green things squared, you're minimizing the sum of the red things squared. So you can actually phrase principal component analysis from a maximization or a minimization perspective. And it turns out to be phraseable as a quadratic form. And so the right answer for this subspace is just an eigenvector. Okay, so it's the principal eigenvector of A transpose A, it turns out to be. So just because both of these things relax to quadratic forms, and that's the answer that you get. Okay. So really quick on PCA. PCA is used a lot to understand kind of the shape of a data set. So if you look at a data set, the principal eigenvector, according to PCA, this kind of principal component, gives you kind of the principal spatial axis of the data set. So the data set has the most variation along that axis. And then the second best is the direction of the second eigenvector, and so on. And the eigenvalues tell you how much spread there is along those different axes. It kind of reflects the variance along each of those axes. And so if you have a really, really big first eigenvalue and really small second, third, and fourth, that means your data really does live in kind of a one-dimensional subspace. And so if you go back to like the outer product view, that means that your data really is really well approximated by just this term in terms of outer products. And that's basically what PCA is doing, is if you want to say project into 2 dimensions, you're keeping these 2 things and truncating the rest. That's PCA. And so if your eigenvalues die out really quick, then PCA works very effectively at preserving a lot of the characteristics of your data set by truncating out kind of irrelevant dimensions. Okay. So yeah, equivalently, A is well approximated by just a couple of outer products in that outer product expansion. So PCA actually, it's interesting, the previous examples that we talked about, this one-dimensional embedding using the Laplacian, it turns out that that's basically the same thing as PCA. It's almost kind of, I told you that the high eigenvectors of A and the low eigenvectors of the Laplacian kind of mean the same thing. So you can actually kind of, the mathematics we've been doing may look a little bit different when you look at it from the PCA perspective versus from the Laplacian-based embedding perspective, but it's really kind of the same solution that we're getting in both cases. So it's not like they're really two completely different processes going on here. It's actually pretty similar underlying mathematics. Okay. And then just a couple of notes on PCA before we move on. One thing to be careful about, I guess my main point about PCA is that in a lot of situations, your data is non-negative. So one of our students in biomedical data science has a matrix of so RNAs and how much counts of RNAs. So they're non-negative values. In that situation, your data actually is not centered on the origin. It actually lives up here in the positive orthant of space. And you have to be very careful when you run PCA in this setting, because in that case, the principal eigenvector, it doesn't really describe the primary spatial axis of your data. It ends up kind of pointing at the centroid of your data instead, because it's trying to, that direction captures as much variance of the data as possible from the perspective of the origin. So the principal eigenvector doesn't really mean something useful here. And in fact, you have to be very careful with normalization because the other eigenvectors are constrained to be orthogonal to the principal eigenvector. So even though the principal eigenvector doesn't mean much, it still can move around the other eigenvectors in kind of a bad way. So you need to make sure that you've normalized your data properly in this situation. And typically, we don't use the principal eigenvector, but we use the second and the third and the fourth, which should sound familiar at this point, right? The principal eigenvector has a special interpretation. That's the centrality vector, and the other ones are the clustering vectors, I guess. So be careful if your data is non-negative, because in that case, the principal eigenvector is kind of special, and be careful with normalization. Most people, when they do PCA, they translate their data set so that it's zero-centered, in which case the principal eigenvector does mean something useful. Okay, one other final point, I guess, about PCA. It's highly related to k-means clustering. In fact, it's kind of a continuous relaxation of k-means in the following sense. So k-means clustering is asking you to divide up a bunch of points into k-clusters and find centers for those clusters so that you're minimizing the squared distance from each point to its respective cluster center. So you're kind of minimizing the variance within each cluster. With PCA instead, you are trying to find not k-centers for clusters, but k directions to project along. You want to find a k-dimensional subspace to minimize the sum of the squared distance when you project onto the subspace. So instead of projecting yourself onto a cluster center, you're projecting onto a subspace. And you can actually sometimes think of PCA as maybe a directional clustering algorithm. So instead of dividing up into k-clusters defined by their centers, you're kind of dividing up into k-clusters defined by their directions from the origin with PCA. So you can kind of think about, well, what cluster does a point belong to? It belongs to whichever of those k components it's kind of closest to. So it actually has kind of a nice interpretation. It's very closely related to k-means from a mathematical perspective. In fact, a lot of times people use PCA for clustering by first projecting their data down to a lower dimensional subspace with PCA and then running a clustering algorithm within that lower dimensional embedding of your data. That's a very common thing that people do. Okay, any other thoughts on PCA before I move on?
What type of normalization do we need to do?
What type of normalization? Typically, like in this situation, you pre and post multiply by something that kind of ensures that the rows and columns have kind of unit weight. It's hard to normalize both the rows and the columns at the same time so that they have unit weight, but you can kind of do something that approximates that. So you basically don't want the data to be really, really stretched out in any one direction here.
So the mean zero mean and standard deviation.
Right. Well, like imagine if this data was like super highly stretched out. That would mean that x1 would be kind of like pulled in that direction, which would have a bad effect on x2 and the rest because they have to be orthogonal to x1. So we want x1, if you do the normalization correctly, usually x1 turns into a vector of all ones. It becomes trivial, just like the Laplacian's lowest eigenvector was. And I can definitely talk about that offline with you if you want. So, but normalization is important with PCA. Normalization is important in many different applications. So I have one last application. This one's actually not that crazy to describe. It's a little different than the other ones, but this one is how do you use eigenvectors for kind of ranking or ordering problems? And so the prototypical explanation I have for this is imagine that Clemson student body as a whole appreciates colors to this extent. So the average person at Clemson likes the color orange to an extent of 60%, likes purple 30%, and likes red 10%, which maybe that's even too high. So what if we wanted to figure this out? I want to figure out basically a vector of proportions here that describes the kind of weight or level of importance of these different colors. So I would like to kind of do an experiment, and after the experiment's done, conclude that this is the vector of absolute importances of those colors. So orange across all of campus has like a 0.6 importance. It's twice as important as purple, right? How would you measure that? It's not obvious because sometimes things are hard to just measure on absolute terms. You can say, Justin, how much do you like orange? 7, 12, 3. It's kind of hard to quantify just one of those things in absolute terms, but you can actually quantify things on relative terms pretty easily. How much more do you like orange than purple? You say about twice as much more. So a lot of times it's easy to compare things and get kind of a relative notion of how much more important one thing is than the other, but you can't actually measure one thing by itself. We do this with the NCAA in football. You have teams play against each other in pairs, so you have a lot of pairwise comparisons to go on, but at the end of the day, you want to rank all the teams. So that's kind of the idea, is you're trying to find an absolute ordering based on the result of relative comparisons. So this actually happens a lot in ranking and rating systems. So it turns out that the answer is, surprise, surprise, it's an eigenvector. So if I make a matrix A, which has all of these pairwise comparisons, so the ratio of P1 to P2, that's how much more I like orange than I like purple. Ideally, that was the number 2. I can actually survey a lot of people and make an estimate of this matrix. It's not going to be the perfect ideal matrix, but these numbers are going to be estimates of what the ratios ought to ideally be. And if these entries in the matrix were in fact the perfect values that they should have been, then the principal eigenvector of this matrix would be that vector P of the absolute proportions that I care about. And the corresponding eigenvalue would be n, if this is an n by n matrix. And so since we're dealing with probably an approximation of this matrix, because I've done some experiments to estimate these quantities, the principal eigenvalue may not be n, but the larger it is, the more I believe the results, the more this matrix is kind of judged to be consistent with itself in terms of having this exact sort of structure. Sometimes this is called Satie's analytical hierarchy process. It's kind of a mouthful, but it's a way that you can use eigenvectors to kind of come up with a single ordering based on pairwise comparisons, which has a lot of applications in different domains. So that's basically, I think, the end of the talk. Thank you guys for suffering through that. Any final questions before we wrap up?
Oh, is there like a book or something that you would recommend if we were interested in getting more deep on this?
That's a good question. So is there like a book or what resources? This is kind of why I gave the talk, because I actually have not found the book on all these things. Like I've picked up these things like in bits and pieces from different places, and I don't think there is like one place where all these things are kind of connected together. So you'll kind of see a paper written on normalized cut, and a paper written on random walks and graphs, and papers written on embeddings and Satie's analytical. So you'll find these things described in very piecemeal ways in different places, but I think the connections are usually not drawn between them as much as they could be. And the intuition is sometimes lacking. So they'll give you the math, but they won't kind of tell you what the eigenvectors kind of mean, or the pictures. So if you have specific things, I can definitely recommend references to look at, but I'm not sure there are kind of books that are good. There's maybe one or two that aren't too bad.
I think I'm vaguely aware of like the graph textbook. This, but
there's also, I guess, one thing we haven't talked about is how hard are eigenvectors to compute. It's probably worth mentioning that fortunately the top few eigenvectors are kind of easy to compute, and the bottom few eigenvectors are usually easy to compute. There's a simple iterative process called the power method that gives you those. If you want to get the middle eigenvectors, you better not have a matrix that's too big, because kind of anecdotally it's like n cubed-ish time to find the full set of eigenvectors and eigenvalues for a matrix. So, but if you only need the top eigenvectors or the bottom ones, you can do those really effectively. Google finds the principal eigenvector of the entire web. And so that's a tractable problem. Other questions? Cool. Well, thank you all again for coming and for the insightful questions that you had. So, awesome. Thanks.
hopefully recorded.